So I came from the sunny Israel. It's about 30 degrees now in Israel, and it's also 2 hours ahead. So I woke up this morning, and it was in Israel time, so it was quite early. And I went running on the canal and was thinking about, I'm really excited to be here, and I'm really excited every time I see new HPC cluster. And I was trying to think why is that excitement? And that takes me back to 2003. This is where in Mellanox, we partner with the Virginia Tech in the US. And there was a professor there that says, OK, let me take the latest and greatest servers. At that time, it was Apple servers, so with the IBM power. But he says, OK, let's take the latest and greatest, fastest performing servers that I can get. And let's hook them together with the best interconnect. And if I can place as many of them in the box, if I can make a data center that is as large as I can get, then I can get to the top of the list in the top 500. And that's what he basically did. And in a few months, we managed to get that system. Everything was fresh from the oven. The servers were new. The interconnect was new. And we managed to get to the third place in the interconnect. And ever since then, it's really exciting that with off-the-shelf components, like the Linux revolution, so off-the-shelf components, you can hook them together with the right interconnect, and then you can build a very powerful machine. And that can really enable all the research and the amazing things you're doing here. And with that, I mean, the challenges have substantially gone up, and I'm going to talk about more and more needs that are there for the interconnect to build a very good system. But still, it's really available to build those machines, and they're all built from commoditized and from off-the-shelf ingredients to bring you the best performance to enable those research. So the first thing I'd like to mention is that we managed to get to number 3 in the list on 2003. This latest top 500 list, the top number one computer on the top 500 list is powered by the InfiniBand interconnect, and that's almost 100 petaflop, which is kind of getting very, very close to the exascale. And this is also a remarkable entrance to the top list because it's like 3 times faster than the second number on the list. So this is an amazing entrance. It has 41K nodes, and this is actually going almost close to the limit where the InfiniBand addressing space gets. So it's a very, very large cluster also for InfiniBand addressing, even though now we have the technology even to go beyond those numbers. So those also are available, but those are the kind of challenges of scale that we're getting challenged every day to be able to bring those huge systems there. And if you look at the chart on the bottom right, you can see in the top 500, the first starts with the top 100, then top 200, 300, and so on. You can see that the InfiniBand interconnect really dominates there. And I'll show you why throughout the presentation. If you look at the future, then those are the 2 flagship clusters, 2 flagship HPC machines by the US Department of Energy. They're part of the Coral project, and they're based in Oak Ridge National Lab and Lawrence Livermore National Lab. And they're being built with the InfiniBand interconnect. Actually, those systems really take advantage of the latest and greatest features, and they're based on PowerPC, InfiniBand interconnect, and GPUs from NVIDIA. And those are part of the exascale kind of exascale path where we're going and really enable the best-in-class services. And all those features that we're developing there would be made available, obviously, for the rest of the cluster. So we're keeping pace for everything that we're doing for those large clusters, and we'll also enable them in the small clusters. So in Mellanox, we focus on being able to deliver the bandwidth. Okay, so bandwidth is usually what you measure when you look at interconnect, and you really, really want to make sure that all the I/O bandwidth that is available from the server can actually go out to the network. This is what really enables scaling if you're doing extreme performance. So the inner bus of the machine is PCI Express, and we're going there past Gen Gen 3 of the PCI Express. We're moving forward into Gen 4 PCI Express, and we want to enable all that bandwidth to always go up to the network. And this is where we have the 100 gigabit, and we're looking forward into the 200 gigabit per second bandwidth, which are really important there. And as a company, we deliver all the end-to-end solution for that. And we even manufacture the cables, and we have the cabling link technologies for that in order to make sure that we can be always on top of the latest and greatest speeds to deliver them. And with the speed, now at EDR, we can really demonstrate real application performance benefits of just moving from FDR into EDR. You can see numerous kind of applications with their performance improvement running a different kind of scale. So you can look at Alter structural analysis. You can see about 40% improvement. And then you can see in weather prediction, WRF, you can see 63% improvement. And that continues to grow, 28, 44%, matrix transpose 68, and MPI-FFT about 80% improvement. And that is basically by moving from FDR into EDR, providing better speeds and reducing the latency of the interconnect. But I think this is definitely not enough. I think it's really important, and that brings the scale to the application and enable them to better perform at scale. But we definitely are doing more. So if we look at what has been happening to the compute, and there are so many new things that are coming in, so there is clearly an evolution that happens in the compute. So the first evolution came when they kind of broke those big SMP machines into clusters of computer. That's the and that really enables, for example, those 2003 machines to come up as clusters from off-the-shelf components and being a cluster of servers. But ever since that, the Moorelow kind of couldn't deliver more performance of being able to build a strong core that will still do the work. And this is where they moved in from single core machine into many cores. So it started with 2 cores, and now it's tens of cores. And even then, the GPU concept and the very, very large amount of core machines have evolved. And that really brings more complicated clusters, more heterogeneous clusters. People really want to mix and match different kind of processing technologies and put the right jobs at the right place. And this is where we come with more and more offloads, which really enables those computing elements to really scale together. And the next thing that is coming, when you have those complicated machines, then you really, really need to look at code design. You really need to look at the holistic approach. You need to look at both hardware, software, and application and see how you can together optimize the performance. Because at some point, those tools that you used to do to just reduce the message send or message receive latency, they do the work, but don't do the full work. And you can really optimize way beyond that by using other offload techniques. So this is where we came up with the approach of intelligent interconnect. So before that, the network used to just send and receive messages. And this is where we decided we can pull more communication, more computation into that network so that we can really build a scalable approach. So there are really computations that really match the network. What we realized that there are many applications that are doing collective operations. And collective operation is a classical thing that, from the application standpoint, they want to exchange a lot of data. They have very specific pattern and very specific computation that they want to do. And they want to do it quickly. They don't want to wait a lot of time for the data because most of the applications today are written synchronously. So they don't want to wait for that data, but they have to wait until all the operation really completes. So basically, those CPU will be blocking, waiting forever for the data to arrive. And actually, the libraries are going to work very, very hard to exchange all the messages, perform the data reduction, and then complete the operation. And instead, we kind of push that into the network and doing all the computation inside the network. And that overall reduces the amount of time it takes for a collective operation to complete. So think about it. Instead of doing log-n kind of intervals inside the network to exchange messages and do the computation, every node just sends its data, and the reduction just magically happens inside the network. And when it reaches the top of the tree, all the reduction is done and just being sent to the remote destination. So this is where we introduced the SHARP protocol. SHARP stands for Scalable Hierarchical Aggregation Protocol. And this is available from Switch IB2, and that device is available here in the Bear Cloud. And this is really being able to do all the data reduction inside the switch, so doing adding number, finding minimum, maximum, and doing so many other operations. And we keep improving that approach and bringing more and more offloads into the network. And that really enables order of magnitude improvement in real application performance. So Switch IB2 and ConnectX-4 enable it. And now we're pretty much very close to launching to shipping ConnectX-5 devices, and those devices will further have more and more offloads available. So those are examples of the SHARP protocol. This is a finite element micro benchmark that is actually showing the benefits of the SHARP aggregation protocol. And basically what's interesting to see is that the larger the cluster is, the better the performance improvement is. And we're starting from about 10x improvements on 32 nodes. And as you go up to 8,000 nodes, you can really get a much better ratio of the improvement. This is another example measured by the Ohio State University. This is about all-reduced micro benchmark. And they were trying to run both with SHARP and without SHARP. They were running two different benchmarks, and the results look pretty much consistent. You can reduce the time by factor of 2 if you're using in-network computation. And basically, that's a fairly small size cluster. It's about 18 nodes. But one more note about using KNL and those other coprocessors, even if they're bootable, the importance of offload is really large for those kind of devices, because those devices can do really good computation, but when they come to I/O, they don't deliver the best I/O because they're not optimized for it. So if you look at GPU, look at KNL, and they have many cores, but a single core frequency is extremely low, and this is where they try to do I/O. It's hard for them to do I/O, and the more offload you push there, you can even scale better with those coprocessors. Yet another example of SHARP usage by our commercial HPC, MPI, and SHMEM distribution called HPCX. And again, up to 64 nodes, you can see that we're delivering 2.2 higher performance over Intel MPI. And those performance improvements are really valuable because you can either get more of your cluster, or you can even buy a smaller cluster instead of spending much time on real estate. So I mentioned earlier that the #1 supercomputer really managed to kind of populate the entire address space of the InfiniBand by getting to beyond 40K nodes. And this is where we introduced the InfiniBand routers. And InfiniBand routers are really devices that are implemented on top of Switch IB2. And with those boxes, you can really connect multiple pods of compute and connect them together and still get all the RDMA services and getting the best performance. So you can use it for multiple things. You can use it to really extend the addressable space and hook together way more than 40,000 nodes. And you can really use them for doing other things. So if you're looking at silos or pods that you want to do compute or storage, or you basically want to grow your cluster and connect the legacy cluster to a new cluster, or even have a storage cluster and a compute cluster, or multiple of them, you can really have them separately, and you can connect them. With the InfiniBand routers, still get RDMA across them, and still have each cluster or each pod being managed separately. So each one will run its own subnet management, and each one can have its own downtime and upgrade and software versions, but still they can get RDMA services to those routers. And we believe these routers are really something that will enable better isolation and better connectivity in the future. Plus, it enables us the connectivity of legacy and new stuff together. Cloud. Let's talk a little bit about cloud. What we're seeing is that the whole IT infrastructure is being transitioned into the cloud. So it's going to take a while until everything is going to be clouded, but we see more and more transition into the cloud. Especially if you look at enterprise class or service delivery at very large scale, they're all moved to cloud. And what happens in cloud is that it's very easy to provision things, to get you a copy of a VM, to do a lot of stuff. Everything becomes easy, everything becomes elastic, everything becomes so handy. But what happens is that some people just trade off the performance to get those kind of flexibility. And this is where we come to play with our interconnect. So using technologies like SRIOV and other optimization for clouds and also for containers, we're still able to get you the bare metal performance even though you're running in a clouded environment. So we definitely are looking into the cloud. We definitely are supporting offloads also in a clouded environment. We see OpenStack as a very important platform to integrate with, and we have InfiniBand integrated into OpenStack upstream for quite a while. SDN is definitely a part of every cloud solution, and actually InfiniBand was the first, in my opinion, it was one of the first SDN solutions even before the word SDN was invented. But all the switches from InfiniBand are remotely programmable, and we have the subnet manager, which is also open source software called OpenSM that really manages all those switches. So all the software-defined network there in InfiniBand, it's just, that's the way you do it in InfiniBand. And what we did is we tailored the SDN solution from InfiniBand into OpenStack and have it available out of the box. And with RDMA directly from the VM, you can really see here example of getting to 92.4 gigabit per second on a virtual machine quite easily with very minimal CPU utilization. And you can see on the right-hand side, you can see an OLTP benchmark. That's less HPC-oriented, but that's more of transaction-oriented database. Can get 2.2x performance at half the price per transaction, which really gets you about 4 times better performance. That's due to RDMA and very efficient VMs using our network technology. We're proud to have several quotes, but very proud to have the quote from the Birmingham University. One of the important things that we focus on when we're doing the design is to focus on backward and future compatibility. So we ensure at all levels that every time you build something new with InfiniBand, you can always connect to it. So you can connect your legacy cluster, you will be able to connect your new cluster, and we have several technologies that really enable that. First of all, everything is standard. So we focus on delivering standard, and InfiniBand is a standard that was defined by a consortium, and it's still evolving and adding more feeds and speed. It's standard. So we implement the InfiniBand standard, and then we make sure we keep the same API. So we keep the same verbs API. We evolve that API, we add functionality, but we never break existing application. And last, we have the InfiniBand routers, which really enable connecting multiple silos or multiple pods of compute and storage and really scale beyond that. So that's an important characteristic of the InfiniBand, and we keep that moving forward as well. And that's pretty much it. There are many technology we're focusing in Mellanox. I think deep learning is deep learning and big data are coming. They're kind of taking a lot of the technologies from the HPC and leveraging them. The training algorithms using collective, and there are many implementations for that. And we look at offloading them and getting the best performance. We know several use cases for deep learning that all of them are using in very large scale at the web and cloud giants. They're all using the InfiniBand to really scale and deliver the best performance for deep learning. And we're seeing also the HPC community come and use the HPC tools because they're good at scale. And leverage our offloads to make the best machine learning technologies and machine learning system. And that's pretty much it. So I'm here between you guys' questions and tea break. It's the UK or coffee break or whatever. So feel free to ask questions. If not, I'll be outside.
Can we pick up questions over tea, Dror?
Sure. So questions over tea, I'll be there.
Thank you.
All right. Thank you very much.